Welcome, good evening, down under. And your talk is about polynomial functors and families parametrized by comonoids. Please go ahead.
Thank you. And thank you to the organizers and the scientific committee for giving me this awesome opportunity to present to you all today. So as was said, I'm going to tell you about how the notion of polynomial functors can be generalized from the Cartesian setting to the setting of nice symmetric monoidal categories using the notion of comonoids and comodules. So to begin with, I'd like to paint a picture of where this work fits into some existing works. So the notion of polynomial functors is has been of quite interest to the category theory community of recent times. And I guess the most general setting that that most people consider polynomial functors in at the moment is this setting of nice Cartesian categories. So usually that's a locally Cartesian closed category, although Weber sort of did things at a slightly more general in a slightly more general setting in a category with pullbacks, but then had to deal with this notion of exponentiability. So morphisms for which the pullback functor has a right adjoint, and this notion of lax pullback complement, which Weber also called a distributivity pullback, for characterizing when morphisms are exponentiable and dealing with composition of polynomials. So we have this nice setting in which we can think about polynomial functors. Now let me talk for a bit about this other setting. So the category of vector spaces over a field is very much not Cartesian when we use the usual tensor product of vector spaces. And Grunenfelder and Perret in a paper in 1987 asked us to think of coalgebras as the appropriate objects for which to index families of vector spaces. So in this perspective, a comodule for a coalgebra should be thought of as an index family of vector spaces indexed by that coalgebra. They also define this notion of coflat coalgebra morphism, which corresponds to one for which the co-induction functor has a right adjoint. So this notion sort of is similar to this notion of exponentiability over here. Now, both of these fit in the broader setting of nice monoidal categories. And Aguiar, in his PhD thesis, talked about comonoids and comodules in this general setting, in the notion of co-induction and co-restriction, for the purposes of generalizing the notion of internal category from that inside a Cartesian category to one inside a monoidal category. And sort of lying in the middle here, we can consider symmetric monoidal categories. And Boom, in 2018, introduced this notion of relative pullback of comonoids, which is not a real pullback, but it satisfies some pullback-like properties. And in particular, for co-commutative comonoids is a real pullback. And so the point here is that the category of co-commutative comonoids is an appropriate category for indexing. And so what I'm going to tell you first today is that these nice symmetric monoidal categories are indexed by their co-commutative comonoids, and this indexing generalizes the self-indexing of the nice Cartesian categories and the coalgebra indexing of the category of vector spaces. And then next, I'll briefly mention, although not go into too much detail, this notion I'm calling a lax co-induction complement, which generalizes the notion of lax pullback complements in the Cartesian case, and a corresponding notion of exponentiability, which specializes to both exponentiability in the Cartesian case and coflat coalgebra morphisms in the vector space case. And then finally, I'll say how to use this to bring polynomial functors from the Cartesian setting to the symmetric monoidal setting. Okay, so let's start by talking about this comonoid indexing of symmetric monoidal categories. So we want to generalize from the setting of a nice Cartesian monoidal category to a nice symmetric monoidal category. So first, I'm going to generalize the indexing category. So in the Cartesian setting, our category is indexed by itself. In the symmetric monoidal setting, the appropriate indexing category is this category of co-commutative comonoids in V. Now, I think the main point here is that if V is Cartesian monoidal, then this category of co-commutative comonoids in V is just isomorphic to V. And so in that way, this category does generalize the corresponding situation in the Cartesian setting. So next, I want to generalize the category of J-index families for an object J of C. So in the Cartesian case, that category is this slice category over J. Now in the monoidal setting, the appropriate generalization is this category of J comodules for a co-commutative comonoid J. So a J comodule is an object of V equipped with a J coaction. And again, if V is Cartesian monoidal, then this just amounts to a morphism from the object into J, and thus we get an isomorphism between this category of J comodules and just the slice category V over J. And so this does also generalize what's going on in the Cartesian setting. So next, I want to tell you about the re-indexing functors and the index sum functors, but I'll tell you about the index sum functor first. So in the Cartesian case, index sums are given by composition with morphisms in C. So if I have a morphism in C from J to K and an object over J, then the index sum composes that object over J with the morphism to give you an object over K. Now, the appropriate notion in the monoidal case is this notion of co-restriction, which just plugs in your comonoid morphism into the coaction in the appropriate position. Okay, so we have what is going to be our indexed sum functors, but let's now talk about the actual re-indexing functors. So our assumption on our category C in order to have these re-indexing functors was that C has pullbacks. Now in the monoidal case, we're trying to think of this tensor product as some kind of replacement for the Cartesian product. And so I guess if we see pullbacks as really being formed from products and equalizers, we're going to replace the product with a tensor product, but we still need the equalizers in order to form the appropriate generalization of pullbacks. So these are the assumptions that we need. And then under these assumptions, so in the Cartesian case, we have our re-indexing functors are given by pullbacks along morphisms in C. And the appropriate generalization in the monoidal case is this notion of co-induction, which, as I said, can be formed using the co-reflexive equalizers in V and the tensor product. And the point is that, so co-induction does make V into a comon V indexed category. And moreover, we have a Beck-Chevrolet condition relating the co-restriction and the co-induction. And so we have also co-restriction is left adjoint to co-induction. And so we have this indexed category has index sums given by co-restriction. Okay, so finally, so in the Cartesian case, as I've sort of mentioned already in the introduction, it's not always true that for every morphism in C that the pullback functor along that morphism has a right adjoint, but it is useful to consider the case when that's true. So we say that a morphism in C is exponentiable if the pullback functor along that morphism has a right adjoint. And there's a useful notion that Weber called distributivity pullback, but has elsewhere been called a lax pullback complement, which allows us to consider to study these right adjoints diagrammatically. So it sort of is characterized by the co-unit characterization of an adjunction at a particular object in the same way that a pullback sort of characterizes right adjoints to this composition functor at a particular object. Anyway, the point here is that there's an appropriate generalization of this notion of lax pullback complement to the monoidal setting, and it again has a similar relationship to right adjoints to the co-induction functor as lax pullback complements do to right adjoints of the pullback functor. Okay, so that's all I wanted to say about the comonoid indexing of V. So next, I'm going to tell you about these things I'm calling comodule diagrams, which give a nice way of expressing what's going on, the relationship between comonoids and comodules. I'm going to introduce these by example. So here's a picture. For the moment, let's just ignore the colors and the double arrows. We could regard it as just a commutative diagram in our category C. And then we're all familiar with how we can characterize a pullback in a category by a universal property in this diagrammatic way. And I guess for our purposes, we want to think of pullback as giving a functor between slice categories. And so it can be helpful on this diagram to sort of indicate which things are to be, which of the morphisms are to be regarded as objects of a slice category and which slice categories the different pieces belong to. So I guess the next kind of question then is, okay, so we can do this to our diagrams, but then can we use this kind of diagram now to interpret what's going on between comonoids and comodules? And so the answer is yes. So the point here is that we want to think of R here as a comonoid morphism between J and K, and then these double so up the top here. So I'll go back to here. So X and Y are objects of V. G is a morphism of V, and these double arrows are saying that X is equipped with a J coaction, which I'm calling little x. Y is equipped with a K coaction, I'm calling little y. So that gives us a J comodule and a K comodule. And then I'm defining, so I'm going to say that this diagram commutes when this morphism G is actually a K comodule morphism from the co-restriction of X along R to Y. So that's what I'm going to say it means for this diagram to commute. And then we can again consider this kind of universal property. So it makes sense to consider this universal property. And so I'm going to say that such a square here, which satisfies this universal property, I'm going to call it a generalized pullback square for the purposes of this talk. And so the point is, if for every K comodule Y, we have a chosen generalized pullback along R, then this gives us a right adjoint to this co-restriction functor, which I'm denoting here by sigma R. That's our index sum. So in other words, this diagram captures the notion of co-induction, and it turns out it coincides with the way you would define co-induction using the tensor product and the equalizers in V. So so this is all interesting. I guess I should add, so I've mentioned this notion of lax co-induction complement. And again, you can define a similar diagrammatic generalization of the notion of a lax pullback complement diagram, which is then going to have a similar relationship to right adjoints to this co-induction functor. So we can do all this with these diagrams. And I just wanted to maybe give an example of an interesting sort of result that is most nicely stated using these diagrams. So I think we're all familiar with the notion that if I have two pullback squares in a category, then their pasting is a pullback. And so this proposition generalizes this result. So here I have a pullback square in the category of co-commutative comonoids. And then I have one of these generalized pullback squares that I defined on the previous slide. And the proposition says that the pasting of this, so there's a sense in which this generalized pullback square has a pasting, this square has a pasting with that square. And the proposition says that the pasting is one of these generalized pullback squares. So just some comments on this. So the first one is that the proof of this result is more complicated than in the Cartesian case because it doesn't follow from the diagrammatic universal property that I mentioned on the previous slide. you sort of have to use the fact that these things are characterized in terms of equalizers of certain morphisms in the underlying category V. A second thing I'll note is that this proposition is the essence of the Beck-Chevalley property for the adjunction between co-induction and co-restriction, just as the corresponding result in the Cartesian case is the essence of the Beck-Chevalley property between the pullback functor and that composition functor that I was talking about. Okay, so that's all I wanted to say about these co-module diagrams. And I guess, given I said at the start I'd be saying something about polynomial functors, I'd better tell you about those too. So let's just jump back for a moment to the Cartesian case. So here C is a category with pullbacks. I'm going to recall the notion of polynomial functor. So first, a polynomial in C is a diagram in C of this particular shape, where we ask that this middle morphism here be exponentiable. So what that means is that the pullback functor along R has a right adjoint, and that right adjoint is needed to define the associated polynomial functor. So the associated polynomial functor is then this composite functor between the slice categories. So it first reindexes along S, then it does the index product along R, and then it does the index sum along T. And just so we can see why we call these things polynomials, so if we let C be the category set, then we have this isomorphism between the slice category over J and this J index product of set. And then the action of the associated polynomial functor on one of these J index families of sets is to produce this K index family of sets where each component is a multivariate polynomial in the sets that we started with. Okay, so then how does this work in the monoidal case? Well, hopefully from the indexing stuff that I talked about before, this should be fairly clear. So a polynomial in V is now going to be a diagram in the category of co-commutative comonoids in V of this particular shape. And I asked that R be exponentiable. Here I'm defining, so R is in the category of co-commutative comonoids. I'm defining exponentiability in V to mean that the co-induction functor along R has a right adjoint, so that then it makes sense to talk about this composite functor here between the co-module categories. So first co-induction along S, then this index product, which exists by the assumption, and then doing this co-restriction along T. So this is the associated polynomial functor. So, okay, we have the notion of polynomial functor, but to really be able to call these things polynomials, we'd like to be able to compose them. So here, we're going to use, so I've made this assumption that our category V is symmetric monoidal so that we can talk about co-commutative comonoids. And I really wanted to do that so that we could have these Beck-Chevalley-like properties with respect to the pullbacks in the category of co-commutative comonoids in V, because these Beck-Chevalley properties are essential to being able to compose these polynomials. Now, the next thing I should add, so I'm actually adding an assumption to our setup. So if U, the forgetful functor from the category of co-commutative comonoids in V to V, has a right adjoint, so we have co-free comonoids, then one can prove that exponentiability in V, so co-induction along comonoid morphisms has a right adjoint, implies exponentiability in comon V. So in other words, the pullback functor along the same comonoid morphism has a right adjoint. And so putting these together, that means that any polynomial in V, as I defined on the previous slide, is also a polynomial in comon V, as I defined on the slide before that. And so we can compose polynomials in V the same way that we would compose them if we thought of them as polynomials in comon V. So then a natural question to ask is, well, so associated to each polynomial is a polynomial functor, and is this mapping functorial? And I guess my answer is there's a suitable sense in which we can say that index products distribute over index sums. It's the same way that sort of Weber did in the Cartesian case. I think if you understand how it works in the Cartesian case, it should be clear how to generalize it to this setting. And so if we have this distributivity, then the mapping from polynomials to polynomial functors is functorial. Okay, so in conclusion, here are some of the things that I've talked about today. So I told you about this co-commutative comonoid indexing of our nice symmetric monoidal categories and index sums. I also briefly mentioned the notions of exponentiability and lax co-induction complements. And I told you about these co-module diagrams, which are a nice way of thinking about these things. And then I defined a more general notion of polynomial functor in this setting of symmetric monoidal categories. In terms of directions that this can go further, well, at the start, I mentioned this notion of a relative pullback of comonoids by Bohm. And I guess one point I will make here is that pasting result that I showed you a number of slides ago actually holds more generally for not necessarily commutative comonoids, but for only a certain class of co-spans in that category. And so I guess putting that together somehow, so these nice symmetric monoidal categories are actually indexed by not necessarily commutative comonoids, but then we don't have index sums, but for some sort of we sort of have some index-ish sums or something. Like, I'm not really sure what the story is here, but I feel like it would be quite interesting to sort of think about this further. Another thing that I've been thinking about a lot very recently is this category that Spivak calls poly. So these are the single variable polynomial functors in set. Now, this has been of quite a bit of interest lately in the applied category theory community. And I guess I don't have much time to say, you know, what the comonoids and the comodules and all of that are, but an observation that I've made recently is that the bicomodules in this category can be regarded as category indexed families of polynomials. And this really fits with the perspective that I guess I'm pushing in this talk, in that the comodules are index families indexed over the comonoids. So I guess then thinking about, so this category doesn't fit in the symmetric monoidal setting because we're using composition as our monoidal product. And so I guess a natural question is, in what sense this whole setup can be pushed to the monoidal setting? And really the main issue here is the fact that in the monoidal setting, the category of we can't even talk about co-commutative comonoids because we don't have the symmetry. And just the ordinary category of comonoids, it doesn't even like the monoidal product in the underlying category doesn't even necessarily give a monoidal product in the category of comonoids. So it's, I guess the question is, what replacement do we have for Beck-Chevrolet in this setting is really what the question is. And if we were able to solve this question, then perhaps we could move polynomial functors into this setting. Two more things. So I mentioned distributivity of index products over index sums on the previous slide. And so one question is, when does this hold? That's still an open question. And another question I have is whether there are some more examples of categories V which satisfy the conditions that I've laid out. So, I mean, Cartesian V work, vector spaces, and a bunch of categories derived from vector spaces, such as the category of coalgebras work, but I'd love some more examples. So here is my email address. If you'd like to know more or have any ideas about any of the following, I'd love to hear from you. And I'll also stick around in the break, in the next break, in one of the breakout rooms if you'd like to chat there. So thank you.
Thank you, Matthew. Do we have some quick question? Question online?
Can I go on? I don't hear anything.
I can hear you, yeah.
Okay, hi, Matthew. Thank you for this very nice talk. I wonder, you shift from the Cartesian setting to the symmetric monoidal one. Is there really a necessity to work in a symmetric category and not braided? Or you just are in symmetric in order not to, think too much about braiding or braiding inverse?
Yeah, so I mainly haven't been thinking about braiding so that I didn't have to think about braiding, but I imagine a lot of this probably could work in the braided setting too. I just haven't gone through all of the proofs and really worked out how exactly as you say. But thanks, that's a good question.
Yeah, thank you.
Okay, I'm afraid that we don't have time for further questions, so we'll have change over within 2 minutes now. Thank you again to Matthew for his talk.
Thank you.